Now let us look at some of the important points in the chapter Semiconductor. Here we will start with introduction, followed by discussion about main points in PN junction, diode in forward bias, diode in reverse bias condition, and VA characteristics of diode, followed by discussion about main points on transistor and CE transistor characteristics. On completion of this module, we will look at some of the important questions in practice questions session. Introduction about semiconductors. The vacancy created by movement of electrons is called holes. In case of intrinsic semiconductor, number of free electrons is equal to number of holes, and total current in an intrinsic semiconductor, it is equal to current due to free electrons plus current due to holes. At T equal to 0 Kelvin, intrinsic semiconductor behaves like insulator. Also, in case of intrinsic semiconductor, conductivity at room temperature is very low. Let us look at extrinsic semiconductor. In this semiconductor, impurities are added. These impurities are nothing but dopants. This can be categorized into two types, N-type semiconductor and P-type semiconductor. In case of N-type semiconductor, pentavalent impurity is added, and in this case number of electrons is much larger than number of holes. In case of P-type semiconductor, trivalent impurity is added, and in this case number of holes are much larger than number of electrons. At thermal equilibrium, electron and hole concentration can be given as NeNH equal to Ni square, where Ni is nothing but thermally generated electrons. Now let us understand PN junction. There are a few important terminologies which we need to understand in PN junction. First of all, diffusion. Diffusion is nothing but movement of charge carriers due to concentration gradient. The charge carriers could be holes or electrons. The movement will be from higher concentration to lower concentration. Depletion region. It is the space charge region on either side of the junction. What is drift? Drift is nothing but movement of charge carriers due to the electric field set up at the depletion region. Also, let us understand that drift current is opposite to diffusion current, and at equilibrium diffusion current equal to drift current, that is net current is equal to 0. What is barrier potential? It is the potential developed due to loss of electrons by N side and gain of electron by P side of a PN junction. Barrier potential tends to prevent the movement of electron from N side to P side. Now let us understand the working of a PN junction diode under forward bias. In case of forward bias, the P side is connected to the positive terminal and N side is connected to the negative terminal, and direction of applied voltage is opposite to the barrier potential. In case of forward bias, depletion layer width decreases, and hence barrier height also decreases. This allows the current flow to increase in the circuit. Here minority carrier injection happens, and total current in forward bias is equal to hole diffusion current plus electron diffusion current. In case of forward bias, magnitude of current is measured in milliamps. Now let us understand PN junction diode working in reverse bias condition. Under reverse bias, P side is connected to negative terminal and N side is connected to the positive terminal. Here direction of applied voltage is same as that of the barrier potential. Depletion layer width increases and barrier height also increases, and thus the current flow in the circuit decreases. Diode reverse current is not dependent on the applied voltage up to breakdown voltage. If the applied voltage is greater than breakdown voltage, the reverse current increases sharply, and magnitude of current is measured in terms of microamperes. Now let us understand VI characteristics of a PN junction diode. Look at the graph shown here. In forward bias condition, I increases very slowly until threshold or cut-in voltage. This is shown in the first quadrant of this graph. In reverse bias, I is small and almost constant until breakdown voltage. This is called reverse saturation current. This is shown in the third quadrant of this graph. Forward bias resistance is low as compared to reverse bias resistance, and dynamic resistance is given by RD equal to delta V by delta I, that is change in voltage by change in current. Now let us understand two types of transistors, NPN transistor and PNP transistor. In case of NPN transistor, there are two layers of N and there is one layer of P. However, in case of PNP transistor, there are two layers of P-type semiconductor and one layer of N-type semiconductor. The relevant symbols are also as mentioned here. A transistor is divided into three parts. One is the emitter, another one base, and another one is collector. What is a emitter? Emitter supplies large number of majority carriers for the current flow, and it is moderate in size and heavily doped. However, base is thin and lightly doped. In case of collector, the collector is moderately doped and larger in size than the emitter. It collects major portion of the charge carriers supplied by the emitter. Thus, we cannot interchange emitter or collector with emitter. Let us understand some of the characteristics of common emitter transistor. Here input is between the base and the emitter. Output is between the collector and the emitter. Input characteristic can be drawn by varying the base current with the base emitter voltage. That is, input characteristic is nothing but the graph drawn between IB and VBE. And output characteristic is drawn by varying the collector current with the collector emitter voltage. That is, it is the graph between IC and VCE. Input resistance Ri is given by delta VBE by delta IB, where VCE is constant. Our output resistance is given by R0 equal to delta VCE by delta IC, where IB is constant. Current amplification factor is given by beta equal to delta IC by delta IB, and VCE is equal to constant in this case as well. Now let us look at some of the important questions. Question number 1. Explain why gallium arsenide is most commonly used in making of a solar cell. The answer is, a semiconductor with energy gap closer to the intensity of solar radiation will have higher absorption coefficient and hence higher efficiency. For gallium arsenide, this energy gap is equal to 1.53 electron volt. That is closer to the intensity of solar radiation, which is equal to 1.5 electron volt. Hence, gallium arsenide is preferred in making of a solar cell. Question number 2. Why should a photodiode be operated at a reverse bias? The answer is, in reverse bias condition, the fractional change in minority carriers is much larger than the fractional change in majority charge carriers in forward bias. So, effect of intensity of light on the minority carrier dominated reverse bias current is more easily measurable than that in forward bias current. Question number 3. In a transistor, doping level in base is increased slightly. How will it affect collector current and base current? The answer is collector current will decrease as more of the majority carriers going from emitter to collector get neutralized in base by electron hole combination, resulting in increase of base current. Question number 4. Why is it that in a transistor the base region is narrow and lightly doped? The answer is in transistors the base region is narrow and lightly doped. Otherwise, the electrons or holes coming from the input side will not be able to reach the collector. Question number 5. Why negative feedback is not preferred in an oscillator? The answer is the feedback voltage is negative, that is opposite phase. The gain is less than 1 and it can never work as an oscillator. Question number 6. A PN photodiode is fabricated from a semiconductor with band gap of 2.8 electron volt. Can it detect a wavelength of 6000 nanometer? The answer is as follows. To detect a particular wavelength, energy of the incident photon should be greater than band gap energy. Now let us calculate the energy of the incident photon. Here E is given by hc by lambda. On calculation we get energy of photon equal to 0.207 electron volt. We notice that this is less than 2.8 electron volt. Hence the photodiode will not detect a wavelength of 6000 nanometer. Question number 7. The number of silicon atoms per meter cube is 5 into 10 power 28. This is doped simultaneously with 5 into 10 power 22 atoms per meter cube of arsenic and 5 into 10 power 20 per meter cube atoms of indium. Calculate the number of electrons and holes. Given that Ni equal to 1.5 into 10 power 16 per meter cube, is the material N-type or P-type? The answer is as follows. At thermal equilibrium, if Ne is greater than Nh, it is N-type, and if Nh is greater than Ne, it is P-type. Let us understand number of electron Ne or Nh. For each atom doped of arsenic, one free electron is received, and for each atom doped of indium, a vacancy is created. Thus, number of free electrons received is equal to 5 into 10 power 22, and number of holes created is equal to 5 into 10 power 20. Thus, number of electron at thermal equilibrium is Ne equal to En minus Hn. That is, we need to subtract the holes to subtract the electrons that are neutralized by the holes. Thus, we get 5 into 10 power 22 minus 5 into 10 power 20. This gives us the value of 4.95 into 10 power 22 atoms per meter cube for number of electrons. Similarly, number of holes at thermal equilibrium can be found out using the formula NeNH equal to Ni square. Here we know the value of Ne and Ni. Thus, NH is equal to 4.5 into 10 power 9 atoms per meter cube. Since number of electron is much larger than the number of holes, the material is of N-type. Question number 8. In an intrinsic semiconductor, the energy gap is 1.2 electron volt. Its hole mobility is much smaller than electron mobility and independent of temperature. What is the ratio between conductivity at 600 Kelvin and that at 300 Kelvin? Assume that the temperature dependence of intrinsic carrier concentration Ni is given by Ni equal to N0 power minus Eg by 2 kBt, where N0 is a constant. Let us understand the answer here. Conductivity can be given by the formula sigma equal to E into Ne mu E plus Nh mu H. For intrinsic semiconductor, Ne equal to Nh equal to Ni. and mobility of holes is much lesser than mobility of electrons. Thus, sigma can be written as E into Ne mu E. We are neglecting NH mu H value. Also, we know sigma equal to sigma naught e power minus Eg by 2 kBt. Thus, sigma 600 by sigma 300 is equal to e power minus Eg by 2 into 600 kb divided by e power minus Eg by 2 into 300 kb. On calculation we get sigma 600 by sigma 300 equal to 10 power 5, or sigma 600 equal to 10 power 5 into sigma 300. Question number 9. Identify the equivalent gate for the following circuit. Here we have a NOT gate and a NOR gate. The input for NOR gates are A complement and B complement. By De Morgan's theorem, A complement plus B complement the whole complement equal to AB. That is product of A and B. Thus, given circuit is an AND gate. Question number 10. What is Barkhaussen's criteria? The answer is, an oscillator can be described as a positive feedback amplifier. For stable oscillations, the voltage feedback from the output voltage should be such that after amplification it should again become V0. If a fraction B dash is feedback, then the voltage feedback is equal to V0 into B dash, and after amplification its value A into V0 B dash should be equal to V0. This means that the criteria for stable oscillation to be sustained is A beta dash equal to 1. This criteria is known as Barkhaussen's criteria.